Welcome to the Day 1 technical session TS1C Aerosol Air Pollution and Climate Sensitivity of INTROMET 2021. In this session, we have one lead talk by Dr. Suresh Babu, Head of the Aerosols and Radiative Forcing Section at the Space Physics Laboratory of Vikram Sarabhai Space Center, followed by two invited talks by Dr. M. Venkatratnam, heading Aerosol Radiation and Trace Gases Group at the National Atmospheric Research Lab of Department of Space, Government of India, and Dr. Tirthankar Banerjee, Assistant Professor at Institute of Environmental and Sustainable Development, Banaras Hindu University, Varanasi. After the lead talk and the invited talks, we have 5 short oral presentations. This session is chaired by Professor Usha K. Arvind and Dr. K. Satishan. The first chair, Professor Usha K. Arvind, is a professor at School of Environmental Studies, QSAT, and holds immense research and teaching experience with specialization in green technology. The second chair, Dr. K. Satishan, is professor and head of Department of Atmospheric Sciences, QSAT, and holds immense research and teaching experience with specialization in atmospheric physics. The lead talk is for 20 minutes plus 5 minutes for discussion. Invited talk is for 13 minutes and 2 minutes for discussion. And the short oral presentation is for 9 minutes plus 1 minute for discussion. We request the speakers to adhere to the time allotted. The selected questions in the chat box will be conveyed to the chairs by the rapporteurs. Now I would like to request the honorable chairs to kindly take over the session.
Thank you, Shreya. So shall we start now or after 2:10?
So we may start now.
Okay, thank you.
Yeah, thank you. So I think Sir will deal with that. Dr. Satish will deal with that. Yeah.
So welcome all for the session, first session on the aerosols, air pollution, and climate sensitivity. And in this session, we have 9 talks scheduled, and I think I heard that one talk she's not present, so there will be 8 talks. One lead talk will be by Dr. Suresh Babu from the Space Physics Laboratory. And I have immense pleasure in introducing Dr. Suresh Babu for inviting this lead talk. Dr. Suresh Babu is the head of the Aerosols, Trace Gas and Radiative Forcing branch in the Space Physics Laboratory. And his basic interest is in atmospheric physics, and his research specialization is in aerosols, radiative forcing, and climate change. And he has won numerous awards, including Fellow of Indian Academy of Sciences, MOES, National Award of Excellence in Atmospheric Science and Technologies, Shanti Swarup Bhatnagar Award, and he is an associate editor of Journal of Air System Science and a founder member of INSA. He has also received the Swarna Jayanti Fellowship Award and the NASA Scopus Young Scientist Award from the Elsevier Sciences. And these are a few awards, and there are still more awards he received, and I don't want to repeat all of them again. So I invite Dr. Suresh Babu for giving his lead talk. And Dr. Suresh Babu, please.
Thank you, Professor Satishan, for a very long introduction. So today I will talk about aerosol cloud interaction and indirect effect over South Asia. I will share my slide first. Satishan, is it visible now?
Yes, it is visible. You can, with the presentation mode, you can make it in the presentation mode.
Okay. Yeah. So it's in full screen mode now, I hope.
Yeah, but still we are not able to see that in full screen.
Okay. Probably I will do once again and see. I took share screen and share.
Yeah.
Is it fine now?
So you can press F5.
F5. Yeah.
F5. Just F5 will do. So because in
Or
my screen,
you can click on the icon which shows a present slide.
yeah, that's what I did. See, now it's not in full screen. So I have to go there and I clicked on that. So in my PC, it is full screen.
Okay. So that may be.
So when you share, you can share the whole window which is in full screen. You can share.
Okay.
Yeah. Instead of sharing the full screen, you can share the particular application, like my Microsoft presentation PowerPoint.
Sir, firstly, you close the PPT and reopen the PPT, then share this.
Now is it okay?
No, but still we are not able to see. But maybe it's a technical problem. You can, I think, start.
Maybe you could also put it in the reading mode, no? Right hand side bottom, sometimes it appears reading mode. That is also good enough.
Yeah.
The screen sharing is closed. Because in my screen, it is shown your screen sharing is post. How to remove that?
Yeah. Yes.
Now it's fine.
Yes.
Yes.
Okay, thank you. I think I selected some wrong. Yeah. Thanks, Adishan. So I will talk about, I took 2-3 minutes initially, so I will make it fast. Aerosol cloud interaction and indirect effect of aerosols over South Asia. So basically, I will be talking on some of the recent studies which we have done at SPL as part of different scientific programs. Basically, it is observational science programs. So we all know that when we talk about the climate effect of aerosols, we have both direct and indirect effect, and then of course the semi-direct effect also. And the semi-direct effect, where in the recent time we talk in detail because of in the South Asian region, because of the presence of the absorbing aerosols and its involvement in the cloud formation processes. But though we have very good understanding about the direct effect of aerosols over the South Asian region, when we talk about the aerosol cloud interaction and indirect effect of aerosols, though there are a few studies under Ministry of Earth Science and at different agencies, the scientific understanding is in its initial stage, because especially on the observational programs, the database available for understanding this particular physical processes, it needs a lot of context. Some of our efforts I will be sharing here. So when we talk about the aerosol cloud interaction, we know that there was a classic paper in 2006 on whether the size of the aerosol or the composition of aerosols, which is important for the cloud formation, because we know that for the clouds to form aerosols, the aerosols are required for the water vapor to condense. So in that context, I will start with this cartoon. We normally talk about a competition between these two things, whether the composition or size, which is more relevant for the aerosols to form as cloud or the cloud droplet activation. So in very simpler term, we say that the lesser the size, greater the evaporation, and if there are more solute, there will be greater condensation. But theoretically, when we need to do the actual estimations from aerosols, how much cloud drops can form, we know that the theories are well developed even before, along with the theories on the direct effect of aerosols, or even before that, because it involves a lot of thermodynamics understanding of the atmospheric processes. So when we talk about that, we know that the CCN, the cloud condensation nuclei, which are the aerosol soluble or hydrophilic aerosols, which promotes condensation and develop a liquid phase at conditions where the nucleation of pure water droplet cannot happen from its vapor phase. Basically the aerosols provide the surface, but that depends on its hygroscopic nature. So the mathematical formulation of this nucleation process involves the Kelvin effect, which I have written here. And the effect of soluble aerosols is described by the Raoult's law. So combining these both, the Kohler has put forward the excellent theory in 1936 on the Kohler theory, which describes the activation of an aerosol particle into a cloud droplet. So here in the right side, I have shown the Kohler curve for ammonium sulfate aerosols of having a diameter of about 50 nanometer. Using the equations which I have shown here, it is narrated. And I have shown the Kelvin effect as well as the Raoult's law effect in blue and green, red curve. Basically, the Kohler curve is the resultant of these two. So here we can see that the minimum size required for the stable development of the droplet, which is known as the critical activation diameter, and the corresponding supersaturation, which is known as the critical supersaturation. These are two important parameters when we talk about the aerosol cloud interaction. But we know that the Kohler theory was put forward in 1936, around about 90 years back. And there were a few assumptions while proposing this theory, which is the solute matter considered is basically the inorganic in nature, which undergoes complete dissociation, and the dissolved salt does not have a vapor pressure of its own. So to accommodate, but this is not a realistic condition, because we know that to accommodate more realistic conditions existing in the real atmosphere, there were several proposals for the modification of this Kohler curve. So I'm not going through all this, but the recent one was in 2007, because in the real atmosphere, we know that the aerosol exists as a mixture of numerous particles, which involves inorganics, which involves organics. So, and hence it is very difficult to characterize the CCN, means combining all these complexities. So the Patterson and Crendenwies, they have put forward a modification, which is called the Kappa-Kohler theory, which is one of the most important and widely used modification. And so if you have a realistic understanding on the composition and the size distribution of the aerosols, or the size segregated composition, we will be able to estimate the cloud forming capability of the aerosol system and how much cloud droplets can be formed and its further things. So with this background, when we look at the aerosol cloud interaction over South Asian region, we know that there are two major outflows for our region. South Asian region, we have two major outflows. One is the outflow over the southeastern Arabian Sea, which is basically during the December to March period. The northeasterly winds transport aerosols from the South Asian region to Arabian Sea and Indian Ocean. Another major outflow is the Indo-Gangetic Plain outflow, basically from along the Indo-Gangetic Plain to the Bay of Bengal, to the head Bay of Bengal. So these two outflows, when we characterize, it gives an excellent picture of, a very good picture, which is free from the local effect on the aerosols over the South Asian region as a whole. So if you look at, we know that in the recent time, MODIS gives excellent pictures of MODIS and several satellite observations, which involve sea waves, MODIS, then MISR. Even there are several satellites which are giving fairly accurate measurements of aerosols over the oceanic region. But we know that over the land region, the satellite remote sensing is not reliable, but over oceanic region, it's reliable. And all this, the observation shows that the aerosol loading over this region is increasing, unlike the other part of the world, because many places it is reported that it is more brightening, but over our South Asian region, even still the dimming part is continuing because of the enhancement of aerosols. It is mostly of anthropogenic in nature. So for completeness, if you look at the vertical profile of this plume, you can see that the Southeastern Arabian Sea plume, if you look at that mostly aerosols are confined above the atmospheric boundary layer or at higher altitude, even over Bay of Bengal. And if you look at the trend in this vertical profile, you can see that the trend is mostly means between around 1 kilometer altitude. So using this information and the top of the atmospheric flux, which is available from service data, we can estimate the top of the atmospheric direct radiative forcing. And if you look at the direct radiative forcing, which goes almost well in line with the trend with the long-term trend in aerosol optical depth. But if you look at the forcing efficiency, which mostly depends on the composition of the aerosol, there is no significant trend, not like an increasing trend what we normally see in the abundance, which shows that the type of aerosol is not changed much over these years. If you look at the last 15 years of observations. So with this background, we have made some observation from different regions, like the coastal region, which is where our lab is located, Tumba. We have a high altitude station near Trivandrum called Ponmudi, which is around 40 kilometers from here at a height of about 1 kilometer. And we had observations long back from Nainital for an year or so on the vertices at around about 2 kilometers in Himalayan region. So this is just to see that how the cloud condensation nuclei concentration at a different supersaturation or the hygroscopicity of the aerosols vary at different locations. If you look at the coastal region, which can be generalized for the entire West Coast probably, this hygroscopicity is not showing a large variation seasonally. But if you look at the higher altitude, see in the Ponmudi, which is near to the Trivandrum, it shows a seasonal change. So which shows that the observations made near the surface is not sufficient to talk about the CCN characteristics or the hygroscopicity and its cloud formation ability and so on. So in the right part here, I have shown the activation efficiency, means what fraction of the total aerosol system can be act as the cloud condensation nuclei, which we call it as CCN efficiency. If you look at that, we can see even for a particular season, like say winter, which is basically the entire continental region of the South Asia, is basically continental air mass prevails. Even at that time, if you look at between Tumba and Ponmudi, which is we can consider in a synoptic scale, if you look, we can see that it is like a vertical profiling at the surface and at 1 kilometer. The cloud, the cloud nucleation efficiency, CCN efficiency is drastically vary. Near the surface, if it is around varying from about 30 to 50, it increases to up to 60 or 70. The efficiency changes, such a change, large change. So this is one important thing which I would like to convey, that it is very important to have vertical distribution of the CCN efficiency and CCN parameters to get a realistic picture of the indirect effect of aerosols. Another important thing is actually the composition. Initially I have talked about whether size or composition, which is more important. So even at one location, if over a day, if you see, like in Tumba, we have the land breeze and sea breeze effects. During sea breeze, we have, if you look at the inorganic part, the land breeze values are quite high. Organics, it is more organic dominated compared to the sea breeze. But for the inorganics, the variation is not that that contrasting. But if you look at the CCN efficiency, if you see, there is the organics is playing a major role. So the school of thinking of this, the size is more important, or another school of thinking on the composition is more important. It depends on the size segregated composition also. If we try to estimate the CCN from the aerosol composition, we estimate based on Kohler theory. What we found is that the measured CCN and the predicted CCN, or the estimated CCN, it vary because using Kohler theory, we use a two-component system. In one of the cases, we all the time organics present in the atmosphere, but inorganics can be a sulfate or sea salt. So if you look at these two cases here, for lower supersaturation, the sulfate and organics underestimates. But for the higher supersaturation cases, the sea salt and organics combination overestimates. So this shows that this two-component system, which the composition alone or the size alone may not be sufficient. We need to have the size segregated composition when we talk about this. So with this, we had a campaign mode observations on the southeastern Arabian Sea, where we had the observations of the chemistry composition of aerosols and the size distribution, and this is the spatial variation of the CCN observed during that the cruise over the southeastern Arabian Sea during the South Asian outflow. And we try to look at how the CCN concentration and total aerosols how it related. We can see that there is some linear relation exists in some region, but in some other regions, it is regionally, we have given different symbols here. The stars corresponding to the equatorial Indian Ocean, but the southeastern Arabian Sea, this region, we can see that there is a linear relation exists. That means if you know with a single constant, we can find out from the total aerosol what fraction is CCN. But when it goes to equatorial Indian Ocean, such a relation is not existing. And we found that it depends on the geometrical mean diameter or the size distribution of the aerosol. So here we tried to derive an empirical relation and try to find out how it matches. And we found that if you know the size distribution of the aerosols, with an empirical relation, we are able to predict the CCN in the southeastern Arabian Sea, but in the equatorial Indian Ocean, it is not so. So we try to segregate the aerosol system into different sectors, like for the different size distribution regains. So here we can see that the type 6 and the type 2 are the very small aerosols. Here I have shown the smaller particle, mode radius. And for the other cases, it is larger particles, means the mode radius above the 100 nanometer. And if you look at the CCN efficiency, whenever the this size distribution shifted to lower size range, that means whenever there is new particle formation events, the CCN efficiency reduces drastically and it becomes more unpredictable. So another complexity added to the aerosol cloud interaction is actually it depends on aerosol cloud interaction, depends on the type of aerosol from the secondary aerosol formation. When there is more secondary aerosol formation in the atmosphere, the CCN efficiency will reduce and it becomes more unpredictable compared to the other cases. So it becomes a very complex process. And I talked about the altitude distribution in the Indo-Gangetic plain. We have conducted airborne measurements and tried to see how it varies vertically. So this is the supersat, means CCN spectra at different altitudes in three different regions. We conducted experiment from 3 regions. One, we selected region based on the conditions, like Jodhpur for arid aerosols, Varanasi for the Indo-Gangetic plain, and Bhubaneswar for a mix of Indo-Gangetic plain aerosol with the marine aerosols. Here we have a coastal station. So with this, if you look at, you can see that in all these places, the CCN concentration is high. at a higher altitude over Varanasi. But when it comes to the lower altitude, it is the Bhubaneswar values, means mostly it is high. It is basically because of the prevailing meteorological condition. But this is more clear in the NUST graph here. If you look at the CCN activation, the CCN concentration and the CCN activation efficiency, here we can see that to our surprise also, that the Bhubaneswar, of course, is CCN, means the eastern part of Indo-Gangetic Plain, the CCN efficiency is all through the altitudes, it is high. But the CCN efficiency over the central Indo-Gangetic Plain is very low. But if you look at the arid aerosols, like in Jodhpur, it comes in between. So we went to the details of this and we found that it depends on the nature of the dust. Because normally our understanding is that the dusty aerosols are less CCN effective because of its hydrophobic nature. But it depends on the nature of the dust. And here along the Indo-Gangetic Plain, if you see, the central part of Indo-Gangetic Plain, the aerosol system is more hydrophobic than the other aerosol system. So this is basically because of the influence of the anthropogenic black carbon present in this atmosphere. So with this, we try to correlate because when we talk about the aerosol cloud interaction, we know that it is always very difficult to have observations of the cloud condensation nuclei present in the atmosphere and the cloud droplet concentration. And basically these two parameters are required to have an understanding on the aerosol cloud interaction. So here we have done an exercise in the Indo-Gangetic Plain and the different observations which we have carried out over India to calculate CCN from aerosol optics, because this is very much required when we do aerosol cloud interaction from space. And that is for regional studies, that is the only way. If you have to have in situ observations, you have to have very high expensive experimental setup to have observations of both cloud drop size distribution, cloud droplet concentration, as well as the cloud condensation nuclei observation. So we try to see that how the CCN vary with aerosol optics, and we found that there is a good linear relation. So between the aerosol scattering aerosol index or the aerosol index with the CCN concentration, and we try to predict these values, and we got fairly good observation. This was initially proposed by Nagajima in the early 90s, that this can be as a good tool to study aerosol cloud interaction. So with this background, over the both over the South Asian outflow as well as over the Indo-Gangetic Plain, we try to look at how the cloud effective radius vary with aerosol index, where here the aerosol index is taken as a proxy for cloud condensation nuclei concentration. That means the CCN concentration is taken because basically aerosol index is product of the columnar optical depth and size distribution, which is a proxy for the CCN. So if you look at, when we look at the aerosol cloud interaction, it is very important to constrain the liquid water content, because it varies with the liquid water content. So we estimate this variation for different ranges of liquid water path. You can see that from 25 to 50, 50 to 75, and so forth. So here, if you look at this, normally the cloud effective radius is supposed to decrease, means reduce with the aerosol index, because when there are more aerosols in the atmosphere, the cloud effective radius should reduce. But here, what we found is that the aerosol cloud interaction, basically, which is the derivative of cloud effective radius with respect to the CCN. In the case here, we can take it as aerosol index for the fixed liquid water path. You can see that above a critical liquid water path, say 75, we get an effect which is the cloud effective radius reduces with the abundance of aerosols in the atmosphere. But below 75, we can see that it instead of reduction, it increases. So the first case, when the liquid water path is above 75, we call it as it is what we expected, called the Tommy effect. But when the liquid water path is less than 75, the variation of the cloud effective radius means the enhancement of cloud effective radius with the aerosol loading. We call it as anti-Tommy effect. So there are a lot of discussion on the different possibilities for the anti-Tommy effect or the misinterpretation as anti-Tommy effect. And we have gone through the different aspects, and this was published in a scientific reports article. So in that, it was well explained that we have gone through all these aspects, and we could found it that there is something like anti-Tommy effect is existing over our region. So for that, we know that the classic understanding, which I have mentioned now, that when the CCN concentration increases, the cloud drop concentration also increases, cloud drop number concentration increases, and after a certain range, it will be saturated. There will not be, it will be more or less constant. But when there is anti-Tomy effect exists, beyond a certain liquid water conditions, you can see that the number concentration also decreases. That means the water vapor is getting distributed to a smaller, means more accumulated on smaller particles. So to understand this, the most important things to be taken up is now to have particle level understanding of the cloud condensation nuclei. So how it will affect the radiation. So here you can see in the beginning, I have mentioned that how the shortwave flux vary with aerosol index. We get a negative radiative forcing at the top of the atmosphere over the oceanic region. So when there is more aerosols in the atmosphere, more radiation will scatter back to the space, and there will be a cooling in the atmospheric system. But when there is, when the liquid water path is less, when the aerosol index increases, what we found is that the top of the atmospheric flux, instead of showing an increase, it shows a decrease. That means there is more, the less radiation is scattered back to space, and there will be a net warming in the atmosphere. And when the liquid water path is, for the cases when the liquid water path is higher than 75, we found that it is as normal. Like when there is more aerosols in the atmosphere, there is more radiation scattered back to space. This shows that the anti-Tomy effect leads to a heating in the atmosphere. So here, following the paper which is published in 2014 by Chen et al., which is, we found out the intrinsic aerosol cloud radiative forcing over these regions. And we found that for low liquid water path clouds, the forcing is positive, whereas for high liquid water path, it is negative. That means the anti-Tomy effect in the indirect effect of aerosols leads to warming in the atmosphere. That means the enhanced anthropogenic emissions can alter the effect of low-level clouds and affect their energy budgets. And what is the reason for that? So we hypothesize that this is basically an intense competition for moisture when the liquid water path is less than 75. So the aerosols will compete for water vapor, and the more efficient CCN will accumulate, means take up more water and grow in size, and leads to larger cloud effective radius. So for more detailed analysis, we need to have particle level understanding on the aerosols and its cloud aerosol cloud interaction processes, and which is now an ongoing work, which probably in future we will be able to come out with more results. So I took more than 20 minutes. I'm sorry for that. And thank you. Yes.
Yeah, the session is now, thank you. The session is now open for discussion. Participants, please. Any doubts, queries? I think in the chat box. Oh yes, in the chat box there are many, so.
Yeah, I will.
Oh no, it is not for you. There are some other queries, I think.
Yeah.
I have a doubt.
Yeah, please.
Yeah. So does the size of this anthropogenic aerosols affect directly or indirectly the climatic shift or the climate change that we observe today? And is that what you were trying to explain with anti-Tomy effect?
Yeah, basically the anti-Tomy effect is our classical understanding is that when there are more aerosols in the atmosphere for a fixed water vapor conditions, when the number of aerosol increases, the water vapor gets distributed to large number of aerosols, and the cloud droplet size reduces. And there will be more brighter clouds, and the cloud lifetime also increases, which reflect more radiation back to space, and there will be more cooling in the atmosphere, which is the classical Tomy effect. But when we segregate it in terms of liquid water path, when the liquid water path or the liquid, the water vapor in the atmosphere is below a certain threshold value, Here we found that the LWP below 75. What happens when there are more anthropogenic aerosols in the atmosphere? Instead of a reduction in cloud droplet size, we can see that there is an enhancement. It is basically because when the water vapor is less, the anthropogenic aerosols will attract more water vapor, and it won't share the water vapor with other particles, and those particles which already got the water vapor will accumulate more water vapor with that, and the cloud effective radius increases. So what will happen is actually the net effect is, instead of cooling in the atmosphere, it is supposed to generate a cooling in the atmosphere. Instead of that, it creates warming in the atmosphere, and that is the net effect of that. So this is a special condition. This is not the condition always exists, but this we have seen in the South Asian outflow as a new observation. There were such similar observations were found elsewhere, but not in a widespread condition. So when we talk about the indirect effect of aerosols, this anti-Tommy effect also need to be considered. That's what I try to convey to this community. Ma'am, you have muted, it seems.
Yeah, sorry. Thank you, sir. Yes, participants, any further queries? If there are no further questions, let us thank the speaker. Thank you very much, sir, for a very nice presentation and a very interesting lecture.
Thank you.
Thank you, sir.
Yeah, I would like to invite Dr. M. Venkateratnam now for a talk.
Yes.
Good afternoon, Dr.
Yeah, good afternoon. Am I audible?
Yes, you are audible.
Yeah. Should I share the screen now?
Yeah, you can switch on your camera first, and then so that let everybody.
Okay, 1 second. Is it okay?
Yeah. Just let me introduce. Actually, I am very privileged to introduce Dr. Venkateratnam. He's we were actually working in the same lab for sometimes. I was going there for my PhD work, and Dr. Ratnam was there as a helping us a lot at that time. And now Dr. Ratnam is a scientist at the National Atmospheric Research Laboratory, and among his achievements, he is a recipient of Shanti Swarup Bhatnagar Award, and he has a number of publications in the very reputed journals. And today he is talking about long-term pollution exposure and mortality changing patterns in aerosol vertical distribution over South and East Asia. So I invite Dr. Ratnam for this talk.
Okay. Yeah, thank you, Dr. Satishan, for your nice introduction. Am I audible?
Yes.
Yeah. First of all, I would like to thank the organizers for inviting this talk. Then I also want to thank my previous speaker, Dr. Suresh Babu, who has nicely introduced to this topic. So half of my work has been done by him for the basic introduction. Now I'll be talking on changing patterns in aerosol vertical distribution over South and East Asia. And with this slide, I want to try to introduce what is known right now. In fact, role of aerosols, I no need to emphasize for this audience that it is very, the aerosol emissions are integrally linked to society through transport, industry, health, and other factors. And these aerosols have a lot of impacts, particularly on temperature, precipitation, extreme events, monsoon cycle, freshwater availability, and air quality. And using long-term observations, this slide I have taken from Samset et al. Nature Geoscience published in 2019. From the Modi's observations, what they did is the 4 years ensemble mean from 2010 to 2013 minus 2015 to 2018. Here we can see there is a dipole pattern in aerosol optical depth, where there is an increasing trend over India and there is a decreasing trend over China, particularly east part of China. And any change in this kind of aerosol may have a lot of climate-related impacts, and thus it's very important to investigate in detail what are the cause and roles of these long-term changes. But to our surprise, when we have observations over ground-based observations over several places in India, and this slide shows the black carbon concentration over Gadangi. Gadangi is in southern East Peninsular India, where it is shown with a star mark in the left map. And we were surprised to see that there is a consistent decreasing trend in the black carbon. Whereas in my previous slide, the bodies, it was showing that there is an increasing trend in over complete India, except not the west part of India. But to our surprise, that BC now it is showing the last 10 years of data, it is showing that the consistent decreasing trend over Gadangi. This is in Southeast Peninsular India. But this is not only at Gadangi, and our SPL group has published in GRL that by using the RFE network, almost like more than 25 stations having more than 10 years of data. And this slide is taken from Manoj et al. From SPL. You can see the top panel, that Trivandrum, there is a consistent decreasing trend in the last almost like 20 years. And not only in Trivandrum, but also over Peninsula, complete India. And complete Indian region, it is more decreasing trend we have seen. So this is not at all a surprise. Though Gadangi is the one station we have seen the decreasing trend, but throughout India, this decreasing trend is being noticed. So then we thought, where went wrong? So satellite observations are telling that there is an increasing trend in the aerosol optical depth, whereas institute observations are telling there is a decreasing trend. Now, to address this issue, what we have taken is we want to see whether there is any change, because MODIS will give the integrated aerosol concentration, that is called AOD. And if at all any change is there throughout the column, so that should be affected in the AOD. Whereas what we have seen from the surface observations is that in-situ observations within the boundary layer more or less represent the boundary layer altitude. So now the question is whether there is a change in the total vertical column distribution. So now, as my previous speaker, Suresh Babu, has mentioned very clearly that vertical distribution of aerosols is very, very important. Now we would like to see whether there is any change in the vertical distribution in the aerosol concentration. As I no need to again reiterate this one, suppose if there is a scattering type of aerosol, then the cooling is expected at the surface, not only the surface, below or above the aerosol concentration. Suppose that absorbing type of aerosols are there, like elevated type, so that there will be warming and below that will be cooling. But if that absorbing type of aerosols are equally distributed toward the atmosphere, then we can expect the warming effect. So the vertical distribution has a lot of implications. And not only for the test, it has many factors. It will be affecting particularly the precipitation, heavy rainfall, all these things, season activity, all these things will be there, as Suresh Babu has already talked in my previous list. So with this motivation, we have two objectives to investigate here. One is the long-term trends aerosol vertical distribution over Southeastern region, and what are the effect of other dynamical and meteorological factors influencing these changing patterns. So before going to that, and earlier I shown the BC, all these things from surface observations, but we have if you want to see the elevated thing, so we need to go for the LiDAR type of observations. And this is our Gadangi again, almost like 8 years of data we have taken. And this shows the climatological aspects of vertical distribution of aerosol from January to December. And the boundary altitude obtained from radius 1 day is also plotted with a red line. And it's very interesting to see that during the winter months, the aerosol concentration is mostly below the boundary altitude. Whereas during the monsoon season, particularly from July to almost September, October, you can see that elevated aerosol layers are persistent over Gadangi. And another important aspect is that below the boundary layer, there is a clean atmosphere. To explain this, that elevated layer, we have used the dynamical parameters where we see that left panel, zonal wind obtained from radius 1 day. You can see that low-level jet persisting during those monsoon months, which will bring huge aerosol from the Arabian Sea and complete southern peninsular India. This kind of elevated aerosols are expected. And at the same time, you can see the right panel, that radiant humidity. So if water vapor is high, again, these are all again transported from Arabian Sea towards peninsular India, and sometimes from Bay of Bengal towards our side. So then there is a huge water vapor increase during the monsoon season. It can also, as the hygroscopic nature aerosol can take that one, and the scattering can be backscatter will be more. So these are this we could explain that the elevated aerosol is mainly due to low level jet persisting, and water vapor will enhance the hygroscopic nature and then backscatter. And as for that below the boundary altitude, if you see that monsoon rainfall will be almost like consistently having both northeast and southwest monsoon over Gadangi, and there is a lot of chances for washout. And since there is no local emissions during that time, so we have not seen much aerosol below the boundary altitude, but persisting elevated aerosol layer is being noticed over Gadanki region. And again, dynamical parameters, if you see the OLR, that is outgoing long radiation, which can be used as proxy for convection, there is a huge deep convection will be there. Any aerosol present in the boundary altitude can be lifted to the higher altitudes. That is another maybe a possibility. So both long range transport and vertical transport can be a reason for this elevated aerosol layer. Then these are the at one station. Suppose if you want to see complete South Asian region, so we need to depend upon satellite. Before that, I would like to show that what is the contribution of below boundary altitude and above boundary altitude aerosol for the total AOD. So here we have separated the boundary altitude below and above and integrated that AOD, and you can see the right panel, the percentage of contribution of total AOD. If you see during the monsoon season, 80% of the aerosol concentration above the boundary is contributing to the total AOD, whereas during winter season it is 80% below the boundary line it is contributing. During the pre-monsoon or post-monsoon transition, 50% of these things. So here what we would like to confirm is that the elevated aerosol layer present has a lot of contribution to the total AOD, and this is from the one site at Gadanki. And not only at up to 80 kilometers, even there is another aerosol layer that atoll we call, popularly called as Asian tropos aerosol layer. This also again persists during June, July, August, September. And this for almost like in Utilis region, this will be persisting. And these are also from my later observations from Gadanki, almost using like 20 years of data. So these elevated aerosol layers has a lot of consequences. So in order to see the total South Asian region, we have taken the Calypso observations. First, we have used the MODIS observations almost like 20 years. We have used AOD and normal NDVI also we have taken. And the Calypso observations also during 2006 to 2018. And for supporting information, we are taking IMD, surface rainfall and surface temperature. And we are from boundary altitude to distinguish the altitude, we have used interim data products. And what we did is, MODIS will give the total AOD right from top of the atmosphere to surface. That we have used first. Then to separate the contribution within the boundary layer and above boundary layer altitude, we have taken the Calypso data. And this boundary altitude is taken from the interim real product. So first we are showing the MODIS, that integrated aerosol concentration, that is AOD. And you can see it's a well-known figure. I no need to say much details about this. As you may see, IGP region, there is huge concentration. And southern India has a less concentration, as Suresh Babu also mentioned in previous talk. And whereas central India and northwest India has less concentration, like similar to the south India. Whereas if you see the China region, northeast China has a lot of huge concentration. Not only at annual, but even if you see the seasonal variation also, more or less it represents the same, but except that June, July, August, Arabian Sea, we have seen more concentration of aerosol. But persistent results, we can see irrespective of season, this high aerosol concentration over IGP and Northeast China is noticed. Then if we want to see this is the trends, just with the linear trends we calculated. So very interestingly, we can see that throughout Indian region, except northwest part of India, you can see there is an increasing trend. Whereas over China, particularly Northeast China, you can see the consistent decrease in trend, and it has some seasonal variation. If you see the right, the 4 panels, particularly in the monsoon season, even in the monsoon season, we can see the increasing trend over central part of India, whereas consistent decreasing trend is there over northwest part of India. These are all linear trends we use, but are these trends are significant? If yes, what is the contribution of? Because the aerosol AOD is the integral part of total top of the atmosphere to the surface. So any change in the dynamical aspect will have the effect on the AOD. So we have to remove that long period oscillation. So in order to get a true trend. So what we did, we have used a multi-regression analysis where we have segregated the contribution of QBO, solar cycle, ENSO. Then we have taken out that all these oscillations. Then we see the residue. So these 4 panels shows the one is contribution from QBO, the second is from ENSO, third one is solar, and last one is the residue. That is a true trend in the AOD per decade. So to our surprise, if you see the central part of India, that QBO coefficient is very, very strong. And even some ENSO is not that strong, but still there is some contribution is there. And even solar coefficient also has a very strong contribution. But after removing these contribution, if you see that the D panel, where you can see there's a statistically significant increase in trend over India, complete India except northwest part of India, and statistically decreasing trend over northeast part of China is clear. So now what is the reason for these strong trends, and is it the same throughout the altitude? Because this mode is a total integrated AOD, then we want to separate whether there is any change in the within the boundary layer altitude or free troposphere or luteus region. Then we use the calypso observations. So this slide, after segregating the aerosol concentration extinction below the boundary layer and above boundary altitude, here we show the day and night above the boundary altitude, the top two panels, and below the boundary altitude, bottom two, both day and night. The boundary altitude is a very important parameter, and this should be cautiously dealt, because there is no single instrument will give the boundary altitude. We cannot use the calypso. Calypso, though it gives the boundary altitude, but we cannot use always, because it is when the aerosol concentration is very low at those regions, we cannot get the boundary altitude. So we used basically for our interim analysis to check what is the boundary altitude, so that from that above and below we are segregated. So the right two panel shows that 8 UC and 20 UTC. You can see that it is during the night time, mostly the boundary altitude is about 500 meters to 700 meters or less than 1 kilometer. Whereas in the daytime, peak daytime, you can see that more or less 2 kilometer, 2.5 kilometer. So we have separated those aerosol extension below and above from the calypso. And we have also removed the first 500 meter, 100 meters in that during night time and 500 meters during the daytime, because there is some artifacts in the calypso observations. After removing those things, then we have applied again multi-regression analysis. And these are all we are showing only the residue here. So to our surprise, in the below boundary altitude, there is still small increasing trend at some parts of India, but there is a consistent decreasing trend irrespective of day and night over China. And again, if you see the above boundary altitude, you can see there is a very statistically significant increasing trend is there for complete India. And again, China is also irrespective of the below boundary or above boundary altitude or day and night, consistent decreasing trend is seen over the China region. So what could be the reason? Then we have used several aspects like rainfall, then the NDVI, and what we could notice is that particularly the northwest part of India, there is an increasing in the agriculture sector, and that agriculture sector is again we have seen that increasing trend in the precipitation, that middle panel B, and these can be one of the reasons for the decreasing trend over northwest part of India. But there is central part of India, there is increasing trend in precipitation, but we have not seen that decreasing trend in the aerosol, because wet scavenging or dry scavenging will be dominant during the rainfall. But we have not seen such activity, because perhaps the break spells. In fact, there have several research studies have shown that though monsoon, the rainfall doesn't have much trend in the total average rainfall, but you can see that break spells are very high. During the break spells, the dynamics will remain same, particularly that low-level jet, which brings a lot of aerosol from Arabian Sea, will be persisting and will be continuing that one. And those break spells will be one of the reasons for the that increasing trend in the thing. At the same time, if you see the OLR, there is a trend, that increasing trend because of changing temperature. In the climate change, more temperatures will give the more convection, and these more convection will give the more vertical wind. If you see the down panel, that FL. So these vertical winds, if at all any the aerosol transported from the long range transport or the regional aerosol, this will be pumped into the higher altitudes. So this one of the reasons, particularly that why there is an increasing in the elevated aerosol, particularly in the free troposphere. We could explain using the dynamical and meteorological aspects. Now, not only this one in the free troposphere, even if you see the calypso observation, these are all from level 0 products, which we have screened after screening out the cloudy days and cloudy profiles. And this is from the calypso, particularly during the monsoon season. And when we combine with the SAGE 2 and calypso, you can see that from 1995 to 2000, the recent one, there is an increasing trend in the even not only in the free troposphere but in the utilus region. So with this, I will summarize my findings. So we have seen the changing patterns in aerosol over Asian region using long-term satellite, both by combining both passive and active satellites. And we have seen that existence of elevated aerosol layers in satellite measurements, and we have confirmed that using from the ground-based measurements. So a very nice comparison is being seen from the ground-based LiDAR and satellite-borne calypso. And we have seen the dipole pattern in AOD, that increasing trend over India and decreasing trend over China. And the most important that one, the northwest part of India, there is significant decrease in trend, and we could able to explain because this is due to increasing trend in rainfall leading to more increasing vegetation or vice versa. And more important that long period oscillations, we have seen very significant contribution from the long period oscillations in the AOD. And this has to be exercised in all the long-term trends. Generally, they will not consider the long period oscillations. Those two has to be removed before seeing any trends. And there is a shift in the vertical distribution, particularly the free tropos and utility aerosols are increasing. And this we attributed to the changing climate, that more convection, more vertical wind, so more upward transport can be happening. So, but the consistent decreasing trend is seen over China, irrespective of, even though there is a warming and vertical wind is high, because of cleaner actions taken by the China starting from 2012 onwards, they could be able to reduce these even boundary layer pollutants itself. Then even the vertical wind is high or the convection is high, they could not able to see that the within the boundary layer free tropospheric aerosols, there is a consistent decreasing trend is there over China. And we could explain that meteorological dynamics are playing important role in the changing patterns of aerosol vertical distribution. However, here we have seen the total AOD, and there is some see, for example, if I see the BC, we have shown the decreasing trend, but here in the total AOD, that is irrespective of BC may be from 20 to 30% of fraction only in the total AOD. But if you see the total aerosol, that chemical composition is very important, as Suresh Babu also mentioned. And those chemical composition, because if we have to see whether scattering type or absorbing type, it is increasing. So that we have to, again, the Calypso will give some information on that. We are working on those things. So more details we can find in this paper published in Nature Scientific Reports. With this, I will stop my presentation. Thank you very much for your attention.
Thank you, Dr.
Yes.
Talk. So now the session is open for any questions.
I hope I'm clear.
Have you found any change in the aerosol distribution during the northeast monsoon season?
Actually, if you see that for the post monsoon, we basically segregate as a northeast monsoon. Yeah. Particularly for Gadangi, that southern peninsular India, and we have seen that there is an increasing trend.
Okay, so is that contributing to the rainfall patterns during
that I do not know exactly, but we are not work, whereas we have to see more closely.
Okay. So if there are no other questions, let us thank Dr. Ratnam for giving an informative talk in this difficult subject of studying the aerosol, because observations of aerosols, especially over the vertical profiles of aerosol, is very difficult to obtain. And the Calypso also is very narrow swath is there, and its coverage is throughout the globe. Within how many days it will be covering?
16 days actually at a given location, it will repeat as at 16 days. But this is if you consider the 0.5 degree by 0.5 degree. But if you increase the 1 degree, 2 degree, it will come to 8 days or 4 days. Okay. At a given location.
Okay. Okay. Thank you once again, Dr. Ratnam.
Yeah, thank you. Thank you very much.
It's nice having you for this talk. So our next talk will be by Dr. Tirthankar Banerjee.
Hello, am I audible?
Yeah. Good afternoon, Dr. Tirthankar Banerjee.
Good afternoon.
So Dr. Tirthankar Banerjee is from the Banaras Hindu University. Is the assistant professor at the Institute of Environmental and Sustainable Development in the Banaras Hindu University, and his expertise is in the air pollution dispersion modeling and modeling meteorology and air pollution interactions, etc. And basically, he's studying aerosols science and its transport, etc. So let us welcome Dr. Tirthankar Banerjee for your talk on long-term pollution exposure and mortality in an urban environment over IG Indo-Gangetic plain, right? So thank you for coming for this talk, and over to you for this talk.
Okay, thank you very much. Am I audible and my slide is visible to all?
Yes.
Okay, so first of all, thank you very much, the organizer, for the opportunity to present my talk. I'll be talking on long-term pollution exposure and mortality in an urban environment over Indo-Gangetic Plain. And then very happy that I'll be actually continuing the ongoing discussion on the aerosol vertical profile, as emphasized by Professor Suresh Babu and Professor Ratnam. But I'll be also concentrating on the aerosol type that we can actually quantify by using satellite data, and how we can actually relate this aerosol type with the mortality that we have done with a statistical model. So the first one that already been discussed, and you all the people have known, that we have different kind of aerosols that are suspended in the atmosphere in a different regional kind of aerosols that like over the US, these aerosols are coming from mostly from the automobile and the wildfire smoke, and where in Africa these are most are coming from the Saharan dust desert. But over India, these aerosols are highly complex and diverse, and that is actually the more constraining because and complicated because in a different seasons and based on the human behavior, the aerosol types and their composition significantly change over the South Asian region. And that actually make a lot of complications in terms of understanding and relating the impact of aerosols on human health, impact of aerosols on climate and other sector. And so this is another complications over this this Indo-Gangetic plain, which is a large and vast plain having multiple sources of air pollutions and aerosols. And these aerosols are highly diverse, as I said, and their compositions actually vary from the northern plain to the eastern plain. And that's why their impact on the climate change and regional biodiversity, regional agricultural productions are very much complex. So by this means, this presence of this aerosol, so by the entire Gangetic plain is very much providing the uncertainty for the food security, human health, and overall the sustainability of the region. Now, this is the entire Indo-Gangetic plain, where we actually, this region, we actually, just let me take this laser pointer, yes. So this is actually the Indo-Gangetic plain that I am actually emphasizing. This region is having diverse and this aerosol optical depths actually changes with season. And you can find that more of the aerosol optical depths you can find over the eastern part. And these aerosols are typically absorbing kind of aerosols and UV absorbing aerosols. And these are mostly in the fine particulates. Now, recently we have analyzed some of the source apportionment studies that are being done by using receptor model using the ground-based data of PM2.5 measurement and their composition. And by analyzing those source apportionment study, we have come to know that overall over India, the vehicular emissions are the most important source of PM2.5 at the ground level. And beside the vehicular emissions, region-specific other sources like industrial emissions, secondary aerosols, and the biomass burning contribute to this fine particulate concentration in the atmosphere. And if you have make some kind of idea that how much fractions this vehicular emissions contributes, we can say that overall 37% the PM2.5 present in the atmosphere is being contributed by the vehicular emissions, but also the biomass burning and residential burning also almost contribute 18%, but it actually vary significantly in spatial and temporal scale, like in different season and different region, it's very significantly. Now, this IGP or Indo-Gangetic plain is also very important in the context of South Asia because it contains a massive burden of the aerosol optical depths. If you compare it against the other part of the India, that overall this, if you make an annual average of aerosol optical depth from the MODIS, it has almost 0.50 AOD in compared to the global average of 0.13. And this AOD is significantly high over the eastern part, where this AOD may reach up to greater than 0.80, during the typical winter and post-monsoon months. Now, among the, as I said, among the different sources of aerosols over this Indo-Gangetic plain, one of the important sources is the biomass burning, and that has been regularly discussed over the different platform. And nowadays, is an important issue over the Delhi NCR and over this Gangetic plain, because of the stubble burning, which are left in the agriculture field. And we typically have two times where we have experienced this kind of biomass burning episodes, where practically one during October when rice residues are being burned, and then typically during a mid-May where wheat residues are being burned. But the difference in terms of active fire counts, the number of fire counts that actually happens during these two periods are quite vary. Like you can find in this figure that the number of fire counts during April, May is very low compared to the October, November, when rice is being burned. And that rice burning is produce huge amount of carbonaceous aerosols that actually make the context of my discussion, that how these carbonaceous aerosols, specifically the black carbon aerosols, constitute a negative impact on the human health. Now, this is being this figure is coming is taken on the November 11, when you can find that November 11, 2021, that you can find that this red spot indicate the active burning fire spots, and this white this areas is showing the how this smoke is coming from these active fire spots towards Delhi and in the Agra and other Gangetic region. Now we have made some analysis when we compare that how much this biomass burning is actually contributing over this Gangetic plain. And you can find that by using the MODIS data, by using the UVI data from the ozone monitoring instrument on onboard Aura satellites. And you can find that we have divided this region in this period, temporal period, in two contexts. In one is when the biomass burning is extremely dominated, that is from 15 November to almost December end, and the rest of the period when the boundary layer is almost lower and the pollution effects are higher, that is from the October to 15 November and the entire January month. So the entire period from October to end of the January is actually we experience a lot of biomass burning, but at two different purposes. One during October, November, when the rice residues are being burned, but during the winter period, basically this biomass burning happens due to the for generating heat, because this is a very cold region, and it's a common practice over this in the village and in the cities also to burn wood for generating heat. Now, if you can compare these two periods, this one is the biomass dominating period, one is least dominating period. The variation of the AOD over this IGP, Indo-Gangetic plain, is not so much significant. That is 0.55 and 0.53. And even the Armstrong exponent that actually indicate the type of aerosols. So more higher the Armstrong exponent, that you can consider is the finer aerosols. So the aerosol type does not change, but you will find that UV air or the ultraviolet aerosol index, that is the absorbing nature of the aerosols, is significantly increased from 0.99 to 0.77. And other tracers of the biomass burning, like carbon monoxide, is also increased during this extreme biomass burning period. And you can find out that the huge amount of carbon monoxide is actually present over this entire Gangetic plain. So that actually indicates that from the burning of the biomass, it actually emits a lot of trace gases, specifically carbon monoxide and carbon dioxide and other carbonaceous aerosols, which potentially have a very high negative impact on the human health and also the climate change. Now, beside this spatial distribution of the aerosols, as discussed and emphasized by the Professor Suresh Babu and as discussed by the Professor Ratnam, we are also thrilled to understand that how this variation is actually happens over the vertical scale. Before saying that, let me also emphasize that beside this biomass burning, there are other sources over this region. That is, you can see this is the image being taken on November 12, as posted by the NASA websites. You can find that dust plume is also coming from the Sahara Desert. So that actually again make it complications that the aerosol optical depth may change or may not change in the long run, but the type of aerosols or what is the aerosol type or constituents may significantly change over a temporal scale. So, and another important factor that I also wish to emphasize, that the meteorology, that the regional meteorology over Gangetic Plain is also contributes significantly in terms of regulating the aerosol optical depth, the pollution concentration, because most of the time these are being is a tropical region. A subsidence occurs over this Gangetic Plain, and that actually helps to bring all the pollutants from the upper Gangetic Plain, from the Pakistan, Punjab, Haryana regions towards this central and the lower Gangetic Plain, and that helps accumulating these pollutants over these lower and the central Gangetic Plains. So you can find this figure in the third one, that clearly the westerly is actually accumulating these pollutants from the upper Gangetic Plain and being transferred towards the central and lower Gangetic Plain. And despite not having a regular and industrial sources over this central and lower Gangetic Plain, pollutions that is actually originated from the long range, coming from the long range transport from the upper Gangetic Plain is actually accumulating over this central and lower Gangetic Plain. Now, as I said, as these pollutants are actually accumulated, these are actually distributed across the height. Now, these figures from the Calypso clearly indicate that over the height, these pollutants and their types are actually changes. You can find that close to the surface, near the surface, these pollutions are mostly polluted continental aerosols, which are actually black carbon aerosols, carbonaceous aerosols. But as you go to the top, at almost a 5-kilometer height and so on, you will find there's a complete distinctions of the aerosol type that are present over these regions, and there is a presence of the dust aerosols. So both these aerosols will generate some amount of AOD, but their implications on climate, regional meteorology, cloud formations, and also on human health will significantly vary. So that is one of the important aspects that we're actually looking forward to identify, to use the satellite database to accurately identify the type of aerosols that are present at the surface level, so that we more accurately quantify that which aerosol type is actually contributing how much amount of negative health impact in terms of mortality. Because we hypothesize that if there is a significant amount of dust aerosols present in the atmosphere, that may not contribute to that amount of negative impact. If there is a higher amount of carbonaceous aerosols, specifically black carbons and organic carbon, these aerosols are present, they are more carcinogenic and they can produce more negative impact. So our target was to characterize the aerosol type that are present near to the surface and how these aerosol layers are actually stratified across the atmospheric column. Now this figure actually indicates that only for the summer month, that is including the June month, because during June, we have very less rainfall over this Gangetic Plain, because although monsoon start from the early June over the southern region, but over the June we got little rain over this Gangetic Plain. So we took this from March to June for the 10 years, from 2010 to 19, and you find that the type of aerosol using the MODIS and OMI collocated observations for these 10 years, you can find that how these aerosol types are actually distributed over different urban hotspots, like over the Karachi and Multan, these over the upper Gangetic Plain. These cities are having more dominating dust aerosols. But as you go towards the central and the lower Gangetic Plain, the contribution of the smoke and urban aerosols are typically the mixture of dust aerosols and the carbonaceous aerosols. So the contribution of the smoke and urban aerosols clearly increasing, and at Dhaka, the contribution of this aerosol type, like specifically smoke and urban aerosols, are significantly high compared to the dust aerosols. So the contribution of the dust aerosols over these regions gradually decrease from the western semi-arid dry region as you move towards the eastern plain. So this figure clearly indicates that how the aerosol types are actually changes over the different urban hotspot. Now we have also tried, by using the Calypso database, we also tried to how these aerosol types are actually stratified over these urban hotspot, and you'll find that on a different height, like this over the Karachi, this 0.82 indicates the aerosol optical depth measured by the Calypso during the summer month. This entire data set is on for the summer month, and we're continuing over the other seasons also. You'll find that 55% of the Calypso AOD is present at lower than the 1 kilometer height. and 20% presence at 1 to 2 kilometer height. So it clearly indicates that over the most of the urban hotspots across the South Asia, aerosols are clearly present below the 2 kilometer, maximum 3 kilometer height. So that means most of the aerosols are remaining close to the surface, not at very close to, but it is actually spread from surface to 2 kilometer or 3 kilometer height. And if we classify these aerosol types, that what kind of aerosols are present at a near to the surface. So figure B indicates that what are the types of aerosol that are present below 1 kilometer height. Now you'll find that over Karachi, 57% of the aerosols that are present at below 1 kilometer is of dust aerosols. Now, as you go from Karachi to Multan, and then you go to Lahore, Delhi, Kanpur, and Banaras. So as you go from the upper Gangetic Plain to the middle and the lower Gangetic Plain, you'll find that the below 1 kilometer, their significant contribution is being done by the dust aerosols. Almost 57 to 66% of aerosol AOD is being contributed by the dust aerosols. But gradually, the polluted dust or urban aerosols, which are typically indicate the presence of smoke, and dust aerosols, road dust, the mixture of these aerosols, their concentration, their contribution to the AOD below 1 km significantly increases. And you find that over from Delhi, Kanpur, and Banaras and Dhaka, over these smoke aerosols and their contribution significantly increases, and they contribute maximum portion of the aerosols loading below 1 kilometer height. So that is our hypothesis, that over different stations across the South Asia, the aerosol optical depth may or may not vary significantly, but the presence of aerosol type may certainly vary significantly. And that will depend on both two factors, that is the regional or local emission sources and the presence of and the kind of meteorology that presents over this region. So taking these observations over a spatial scale, we have tried to understand that how these air pollution, specifically the trace gases like carbon monoxide, nitrogen dioxide, and other gases, and air pollution is actually contributing to the negative impact, specifically on the cardiovascular and pulmonary diseases, neonatal conditions, bronchitis, all these, and asthma, how these aerosol types and their trace gases are actually contributing towards the mortality. So we have, because we understand most of the concentration, most of the air pollution and mortality based research work are actually depend upon the PM2.5 concentrations or the aerosol optical depth measured on a satellite. But in general, they do not use the aerosol type into their model, and that actually relates some kind of uncertainty in terms of how these aerosol types are actually contributing to the mortality. And that actually these researchers actually generalize all the airborne particulates into equal toxicity, but these are actually not true, because the aerosols which are coming from the combustion sources like combustion of the wood, residential oil, coal, and petroleum, they are actually produce carbonaceous aerosols which are far more toxic and produce far more negative health impact compared to those particulates which are coming from the non-combustion sources. So considering this, another important factor that we took into consideration, that what are the major sources of these carbonaceous aerosols, specifically BC aerosols. Like over India, these BC aerosol, black carbon aerosols are actually coming from the burning of biomass or biofuels, but over the US and European countries, these are mainly automobile emissions actually contribute these kind of black carbon emissions. So in our research, what we took data from Central Pollution Control Board on aerosols data, we do black carbon data, and we relate statistically with the all-cause mortality of collected from the municipal corporation on the Banaras city. And then we use semi-parametric quasi-Poisson regression model with some confounding factor like temperature, relative humidity, long-time trend, seasonal trend. And we took this as a potential confounder, and we actually relate that how these air pollutants like trace gases and aerosols are actually contributing towards the human mortality. And we also compare these on the terms of age and no age days. So what are the data they have compared? We used daily mortality data from municipal corporations of Banaras. We have classified this mortality data into date and cause of the death, their gender, their age. We also classified this mortality in terms of non-accidental mortality, cardiovascular and respiratory diseases. We have classified in terms of their age. We took meteorological data from IMD stations located inside the Banaras Hindu University campus. We took air quality data from the CPCB station that is located inside the Banaras city. We took PM 2.5, PM 10 concentration, NO2, SO2, and ozone from 2009 to 2016. And we also took visibility data from the meta data sets to classify the entire observation period as a H and non-H period. So with some statistical corrections of data has been done. We avoided the outliers. We use the hourly data and then convert to a daily database. And then we have actually done the semi-parametric quasi-Poisson regression model. We use both the single effect model and the multiple pollutant effect model. We control our model in terms of seasonality, in terms of long-term trend, and also the potential non-linear confounding effects of mean temperature and relative humidity. Also, we tried to include the day of the week and public holiday into the model, but they did not contribute significantly in the model development. And also we have used penalized cubic smoothing techniques, and degree of freedom was estimated by the algorithm for each of the nonlinear components by using the GCD score. We have also considered the effect modification of individual populations in terms of their age, their gender, their place of death, and season in terms of mortality and pollutant interactions. And we have classified the H days based on the standard protocol. So let us discuss about the result that we got. And it's a very interesting and very interesting to say that among the important parameters like the BC, PM 2.5, PM 10, NO2, sulfur dioxide, and ozone, black carbon, which is coming from the carbonaceous aerosols, this is the kind of carbonaceous aerosol, are actually contributing to the maximum mortality to the population. And it indicates that almost 5% increase in the mortality with a 10 microgram per meter cube change in the pollution level of the BC concentration. So that was the single result of a single model, where we find that the most important air pollutant that actually contributing to the human mortality is black carbon for the Banaras city. And compared to after the black carbon, the second important pollutant is nitrogen dioxide. Now, we also classified this mortality in terms of age, in terms of the male and female, in terms of the season. And you'll find that the mortality estimate was particularly high for the black carbon aerosols, followed by the nitrogen dioxide exposure. Both PM 2.5 and PM 10 induced greater mortality risk for the male, where female were more affected by the nitrogen dioxide exposure. And we found that the elderly peoples are most susceptible for the black carbon and nitrogen dioxide exposure. And also we've noted that during winter, significant association of the mortality with the air pollutants. Now, we also try to classify that how these air pollutants are actually making this negative impact by during H and non-H days. Overall, for the entire 8 years of study, we'll find that 68% of the days were actually H days. That means they are more dominated by the presence of PM 2.5 concentration. And there's a huge amount of PM 2.5, that is 62 micrograms, and also the black carbon concentration, that is 9.5 during the H period. Now, this black carbon concentration is during the H period was found to induce even higher mortality during the H days. Like you can find that during the H days, this black carbon aerosols is responsible for 6.11% of mortality for every 10 microgram change in their concentration, whereas during the non-H period, this black carbon was slightly lower in terms of their impact. Beside this black carbon, one of the other important factors that will emerge is nitrogen dioxide. That is also a pollutant, which is co-pollutant, which is coming from the burning of the biomass. So that actually also relate. There's, apart from the BC, nitrogen dioxide is also very important air pollutant that actually inducing significant mortality over this population in the Banaras city. So effect estimates of the PM 2.5 and nitrogen dioxide during H days were considerably high, and both were statistically significant. Now, so overall, we note that the individual effect of black carbon, PM 2.5, PM10, and nitrogen dioxide exposure was very high and statistically significant for the city of Banaras. And that was particularly significant during the period of H, when PM2 concentration of the PM 2.5 is very, very high. Concentration of the nitrogen dioxide is also very high. When you compare, you combine the exposure of the black carbon and other air pollutant, you only found that BC, NO2, and PM 2.5 are actually causing a combined effect, and that time their impact on the mortality is significantly high compared to their individual exposure. And also we found that the higher effect of pollutants during H established for the role of black carbon, PM 2.5, and nitrogen dioxide exposure on the premature mortality. Another factor that we have tried here, but that we hypothesize that during the H days, the H days may come during the winter period, and the H days may come from during the summer months also. But their sources may be different. Like during the winter over Indo-Gangetic plain, this PM 2.5 are actually coming from the burning of the biomass and other energy-related practices. But during the summer month, most of the PM 2.5 are actually coming from the resuspension of the road dust, resuspension of the crustal material that also contributes significantly to the PM 2.5 concentration during summer. So we hypothesize that the constituents of the PM 2.5 during summer and winter will vary, although their concentration may not vary significantly. So we also try to relate that how PM 2.5 and BC is actually making an impact on the human mortality both during summer H period and a winter H period, but no statistically significant variation was observed for the city of Banaras. So now we're actually trying to emphasize that how we could actually use the Calypso observations and observations of the other satellite to predict the aerosol type over the spatial scale over this Indo-Gangetic plain, and we are trying to trying that how best these observations, including the Calypso and other satellite observations, how best these observations can be related statistically with the pollution exposure and the mortality over this Gangetic plain. So with this word, I thank you again, the organizer, and I'm open for the discussion. Thank you very much.
Yeah, thank you, Dr. Banerjee. Any questions? Actually, it was a very informative and discussion about your, and many of the studies are new to for a meteorology people, how the effect of aerosols affects the health, etc. are new to meteorology people, and more type of such studies will be useful. So, any questions from audience? Okay, if there are no questions, let us thank Dr. Banerjee for this talk. Thank you, Dr. Banerjee, for giving a nice talk.
Thank you. Thank you very much.
Let us go to the next talk. Next talk is by Dr. Aditi from MOES. Dr. Aditi will be talking about the role of air pollutants formation of fog in an urban environment of India. Dr. Aditi?
Yeah.
Yes.
Share its.
Yeah, actually, instead of sharing your full screen, maybe if you share your slide.
Yeah, is my slides seen?
No, we are seeing your browser, not your slide.
I'm just trying. Huh?
Ma'am,
Is
first,
it now?
yes, yes.
Yeah.
Yeah. Yes, yes.
So yeah, good afternoon, everyone. So I'll be talking about the role of the air pollutants in the formation of fog in an urban environment. And this work has been carried out by me and by Dr. Mahesh Kumar. So we all of us know that fog is a very plays a significant role in many environmental and the
Just a
processes
minute,
over.
Dr. Aditi. Actually, it is not in the presentation mode what we are seeing here. So I don't know whether you have started in the presentation.
I have started in presentation mode.
But here, what we are seeing is only in the editing mode. Your slides.
Shall I share it again?
Yeah, maybe you can close it and then open. Then it will be better.
Hmm? Is it now in the share?
No.
Hello, ma'am. Slideshow. Drop down the scroll key in right hand side in bottom.
Yeah, whatever she did also is the same.
Full screen.
Yes, ma'am.
No.
Full screen mode.
Now is it? Is the presentation visible now?
Your slides are visible, but not in the presentation mode. So,
This is in the, I can see in the presentation mode itself, but I don't know how.
maybe you have shared.
Ma'am, in bottom down, the fourth option is the full screen mode. Slideshow mode.
I have full screen only. I have done. Where to go? Entire screen.
So yeah, maybe you can share the entire screen. That will be better.
But then it's not coming. Why window only it will come? No? Is it now in the presentation mode?
No.
Madam,
Yeah.
in that presentation, go to the bottom right. There is a full screen mode. Bottom right. There is a full screen mode.
Yeah.
You press it.
Yeah, I have.
No, you have not pressed.
In my presentation itself, no?
Yes, yes. You go to the bottom right side. There is a full screen mode is there. You press it. Bottom right on your slides.
Yeah, next one. Yes. Click the.
This only, no? Fit
No, no,
slide.
no. That's the first one.
This
The
one.
Yes, exactly. You press it.
Yeah, now it's okay.
Yeah,
Wait.
we are not able, because you may have shared in some other may not be you shared the full screen or something other way. It's not.
It's okay. Otherwise, you proceed. I think.
Yeah, you can proceed with this without showing the slideshow. You can change your pages.
Yes, yes.
Okay. So I will start with that.
Yeah.
So we know that over northern plains of India, fog is significant because it plays important role in many of the environmental and ecological processes. And during winter months, it's a troublesome and very common phenomena because due to fog, the reduction in visibility happens, which affects our transport system, causing loss of time and money. So in this way, it is significant to study what are the factors responsible for the formation of fog over the plains of northern India. So when we see how fog forms is, the fog forms whenever the water vapor condenses. So during condensation, we all know that molecules of water vapor, they combines and make teeny liquid water droplets that are suspended in the air. So one of the most necessary condition for formation of fog is that there should be enough water vapor in the air and the atmosphere should be very humid. And because this condition is generally met during the morning time, as the temperature and dew point temperature are almost same, which
Dr.
causes,
Aditi,
yeah.
are you in the full screen mode? Because we are not able to see you changing the slides. So either you can go to that non-presenting mode, yeah, editing mode, and then you can change the screen.
Where it is slide. हाँ? इसमें तो यही आ रहा है, then why it's not?
Yeah, now you can change the screen, change the pages instead of going into the presentation. Yeah.
So this because high relative humidity is generally found during the morning time. So this is the most suitable time for the formation of fog. And besides relative humidity, there are a number of factors which can actually promote the formation of fog. And in urban environment, we also have other factors which can mitigate the formation of fog. So what particulate matter in urban environment do? They act as the condensation nuclei and helps in the formation of fog. And at the same time, the urban heat island also prevents the formation of fog due to increase in temperature and decrease in relative humidity, and also it affects the wind pattern over that region. So we will be studying in this present study. We'll investigate the role of the meteorological condition and the air pollutants in the formation of fog over the Indira Gandhi International Airport, Delhi. And for this, the observations from 2014 to 2020 are analyzed. The observations of visibility, relative humidity, and wind speed are used in the current study. And using the visibility observations, the fog has been identified whenever the observed visibility is reported less than 1 kilometer. And when we see the air pollutants data, we have used the PM10 concentrations over the airport from the SAFAR network. So this plot shows you the total number of days and the number of foggy days occurred from December to February, from 2014 to 2020. So if we see, then we can easily see that in December and February, we get the maximum number of foggy days. For example, in January 15, the total number was 31, but 29 days there was fog. Similarly, in December 15, 31 the total days, but 30 days it was foggy days, and so on in January 16 and 17. So likewise, we see that only in December and January we get the maximum number of foggy days. But when we come to February, the number of days are decreased, are less as compared to the number of days in December and January. They are not more than 15 days most of the time. So the frequency of fog formation is higher during these 2 months, December and January, and not much number of days are observed in February. So these are the 00 UTC observations of visibility, and the whole in whole study, this observations at 00 UTC have been utilized. So when we this slide shows the distribution of visibility in 3 months, December, January, and February, from 2014 to 2020. So when we see in December, in the month of December, we see that lowest visibility is observed during 2014. The median value is around 200 meter, and the median value shows an increase from 2014 to 15, but then decrease again. It is decreased. So, and the highest value is obtained in 2019. So, in December, if we see in 2014, 50% values are less than 200 meter, and median value is not that consistent decrease or increase we can see, but we can see in some years it is increasing. For example, in 2015 it increased to around 500 meter, then further decreased to around 300 meter. Coming to January, if we see, January observed the lowest in 2020, that is median value was around 0, and then highest value was observed in 2015, and then it was decreased in 16, and 17, 18 it was almost same values, but then visibility increased in 2019. So, and then in February, if we see February, most of the values are much higher as compared to that obtained in December and January. The median values itself, you can see in all the years is higher as compared to December and January. And highest value is obtained in 2020, as in January 2020 we got the lowest, but in February 2020 it was highest. So now we want to relate that how the visibility and the meteorological parameters and the concentration of PM10 is related for these months. So we will one by one we will be considering the meteorological variables. One is relative humidity, other will be wind speed, because only these two factors are responsible for the formation of fog. So when we see in 2014, we get the median value itself at 100, and which clearly shows that this was high relative humidity. So the value of visibility was very less during this month, and then further it is decreased in 2015. And but if you see all the values in all the years in December is around more than 95 or equal to 95, and sometimes it is 100 also. Similar case we can see in January. In 2015, the median value was 100, showing that 50% of values were between 100 to 90% RH. And then 16 again, it was decreased, and median value reached to 95%, with 25% values lying between 90 to 95, and further values lying between 95 to 100. And so is the case for 2017. And if we see in 2018 to 2020, the values were relative humidity were very high during January. But when we come to February months, the median value itself is lower in 2015, and which is further lower to 90 in 2016. Only in 2019 and 20 we get around 100% of relative humidity in February. This is the distribution of wind speed, which is also another factor responsible for the formation of fog. Generally, it is seen that for weak wind conditions, we get foggy conditions. So all we can see that for all the months, it is wind speed value is less than, most of the time less than 2 meter per second. In December, we see the maximum value is 4, but minimum is 0, and median value is 1. And then again in 15 and 16, zero wind speed has been observed in December, in the month of December, and so is the case for 18 and 19. In January, similarly, we can see that for 2016, the median value is 0 meter per second, and we don't get median values more than 2 meter per second for any of the year. But when we come to February also almost the values are lower than 2 meter per second. So in and all, the wind speed conditions are almost same for all the months. We don't get much higher wind speed, which is one of the factor which helps in the formation of fog. Now we come to the concentration of PM10 during these months. So it is clear in 2014 we don't have much higher. The median value is around 250 micrograms per meter cube and highest value is around 350. But in 2015 it has increased further and then decreased in 2016 and also in 2017. But in 18 and 19, yes, sir.
Can you conclude now?
Yeah, it's about to. So like that, I'll just take 1 minute, 1 or 2 minutes. And similarly in January, we get the values not more than 400, median values doesn't exceed 400 microgram per meter cube. But when we come to February, we can see the maximum value itself is lower than December and January. So these are the correlation coefficient of visibility with the three different two meteorological parameters, RH and wind speed and PM10. So we see that highest correlation is obtained for RH, which means that high values tends to decrease the values of visibility. But there is a poor correlation between PM10 for all the months, whereas there is a higher correlation for RH, and wind speed also doesn't have that good correlation. So this particular picture shows that slide shows that how they are correlated, and the reason of not getting very good correlation, if we see 100% of RH is causing visibility to drop, and similarly wind speed is not that much well correlated during this month. So is for PM10. We get an increase in PM10, but here it is decreased, and for some cases it is decreased with increasing in PM10, but for some cases it's not showing so that is the reason why we are not getting the correlation for all the years very well. And these are the same thing for January and then February further. So this is the slide which shows.
Please come to the conclusion.
Yeah. So this is the slide which shows the relative mean of the relative humidity for foggy and non-foggy during whole year. So we see that for the foggy days, we have higher values of relative humidity for all the months, whether it is December, January or February. And wind speed doesn't show that pattern. For foggy days also we get higher wind speed as compared to non-foggy days for some in all the months. And so is the case for PM10. There is not much variation in the values of PM10 for foggy and non-foggy days. So these are the conclusions that visibility values in all the months are much more dependent on the values of relative humidity and are not much influenced by the values of PM10. They are always decreased whenever there is the increase in relative humidity, but the decrease in PM10 value doesn't improve the visibility values always. And it also concludes that the reduction of visibility below 100 meter is only due to the formation of fog at 00 UTC, which is largely dependent on the availability of moisture. So the main conclusion is that though pollutants may play important role in formation of fog, but low visibility conditions in the study have been occurred only whenever there is high relative humidity present in the atmosphere. Thank you.
Thank you, Dr. Aditi. Actually, we don't. I would like to have some questions, but since we don't have enough time, we'll go to the next speaker, Dr. Chinmay Jaina.
Yes.
Yeah.
Hello, sir. Am I audible?
Yes. Dr. Chinmay Jaina. Chinmay Jaina is from IMD, and he will talk about air quality early warning system and the evaluations of PM 2.5 during winter 2020 over India.
Can you see the full screen mode?
Yes. You have 9 minutes for presentation and 1 minute for discussions.
Yes, sir. Okay. Good afternoon, everybody.
Good afternoon.
So, sir, I'll present the air quality early warning system. Basically, that evaluation part of that PM 2.5 this winter period in 2020 and 2021 our Indian region. Basically, the direction from the MOES and also our DGM, Dr. Mahapatra sir, and we are collaborating with the Finnish Meteorological Division. We have developed the air quality early warning system for all over Indian region. Because you can see the our this left hand side plot. This is all over Indian region, and I don't know. This is You can see that this is next. We have provide the information for forecasting for 3 days, and then right hand side you can see the CPCB and the air quality index category. You can see that good and satisfactory 0 to 100, and also moderate yellow color, and orange color poor, and very poor, and also severe category. But in our target is the particular not miss in that poor to severe category, and also we can improve the forecasting system for this range. Then this is our modeling setup for the SILAM model, basically system for integrated modeling system for atmospheric composition. And in this model, we have using the meteorological data from WARP model, from IMD WARP model from 3 kilometer, and the boundary condition from SILAM model, and emission, anthropogenic emission we are using from CAMS and also EDGAR, and biogenic emission using from MEGAN, and natural dust and sea salt emission we are using from SILAM model, and also Delhi region we are using for MOS for emission inventory. And this is the flowchart. This is the flowchart of the our SILAM model setup. And then we can first evaluation for the forecast evaluation for all over Indian region. Here we are using CPCB all over India CPCB observation data, also MOS suffer observation data, and also DPCC observation data. Total we have using 225 observation data from CPCB, DPCC, and Haryana state government, and also Punjab state government. Then we have you see that this time series plot of the December to February. You can see that this red line for SILAM model, and also black line. You can see the observation data from CPCB, and you can see this model is capturing very well because it's gradually increasing with PM2.5 level, and also sudden decrease the PM2.5 level. And also you can see that this January model is over predicting, but still model is capturing the increasing and decreasing from PM2.5 level. And we know that how good is good our forecasting. Then US EPA, they have some standard, some Medis et al. 2005, they describe the standard. This fractional bias is plus or minus 15%, and fractional error is less than 35%. Then your model is excellent. Model performance is excellent. And your fractional bias is plus or minus 30%, and fractional error is less than 50%. Your model is considering good, and above that thing, their model is average. And for considering this statistic, we have did that PM2.5 hourly evaluation for first day and second day and third day forecast. You can see this normalized mean bias is within less than 10%, and also normalized mean fractional error is less than 30%. That means this PM2.5 hourly forecast is excellent category. And also we did some evaluation for PM2.5 AQI basis. Then we have seen there also normalized mean fractional bias is less than 5%, and also normalized mean fractional error is less than 20%. And also we have also evaluated our air quality index, basically poor category and very poor category for first day, second day, and third day. You can see here that this normalized mean bias is less than plus or minus 5%, and normalized mean error less is 20%. And also very poor category, you can see that less than 5%, and also normalized mean error, fractional error is less than 10%. That means our performance is excellent for that for hourly PM2.5 prediction, and no significant changes down into first day to third day. And also this for air quality index poor and very poor category, that also very good, very excellent. Then this is all over India. Then I want to go for city-wise, other city, how the performance of the other city, other model setup. Then go to the Bangalore. This is the time series. For the red one is model SILAM model, and of the black one is observation. You can see that the model is capturing the diagonal variability of that that period, the winter period, December to February. And we have also did for that statistics for first day, second day, third day. You can see here this model is normal bias is less than 25%. That is good, and normalized is for less than 30%. And then also same thing we did for Mumbai. It is Mumbai also you can see that model is capturing and also suddenly increasing and suddenly decreasing pattern, and somewhere is the model is under predict and somewhere also over predict. But still that this number, the statistics of that first day, second day, and third day is the normalized mean bias is less than 5%, and normalized mean fractional error is 30%. That means the model is excellent in Mumbai region. Same thing we did for Patna region for evaluation. Evaluation for Patna for December to February, this time series and also statistic. And this Patna statistic is excellent. This is normalized fractional bias is 15% and normalized fractional error is 40%. Then same thing for Hyderabad. You can see that model is capturing the all the time series, but suddenly it just decrease. That also model is capturing and also that capturing the increasing trend on this, and the statistic of the model is very good. This is less than 1% to 5%, and also normalized fractional error is 30%, less than 30%. Then we have also considered Delhi region. Delhi, you can see that model is over predicting, but still model is capturing the trend for decreasing and increasing trend. But some places model is over predicting. But you can see that this overall statistic of the Delhi is the 15%, and normalized fractional error is 41%. Then we did for the Lucknow, and that also model is capturing very well, and also model somewhere is under predict. The model is under predict, and still that we just the total statistics of that normalized fractional bias is less than 20%, minus 20% under predicted, and that is for 42%. Then you can go again Agra, they evaluate, and you can see the statistics for that Agra is the very good. Normalized mean fractional bias is 10 less than minus 10%, plus minus 10%, and also normalized fractional error is 30%. Then we did the skill score evaluation for that only for Delhi region. We have two categories. One is unhealthy category, another is very unhealthy category. Unhealthy category is the air quality index 200 to above, the unhealthy category, and very unhealthy category air quality index is 300 to above. Then we can see the heat rate. Heat rate in unhealthy category is 85 to 90%, and critical success index is 80 to 90%, and the accuracy also very good, and also false alarm is also very good. This is less than 5%. And very unhealthy category, this heat rate is 75 to 80%, and critical index is above 70%, and also false alarm is less than 15%. That means that model is. Then we also did skills for other city also. Then another model setup is we have now running for the very high resolution and air quality model. This is Enfuture model, that is collaboration with FMI. That is the resolution is 30 meters, and using the concentration from the global model from Shillong model, the regional model from Shillong model, and there is the setup. And also this is the now going on experimental mode. And then we have some public dissemination system. You can go to this website for that link, and here we can see that all pollutant criteria, basically PM 2.5, PM 10, ozone, NO2, SO2, CO, and also dust, spatial distribution, and that also forecasting for 3 days, the 72 hour, and also major city region, that also is described here. Okay, thank you.
Thank you, Dr. Chinmay. So any questions? Yeah, if there are no questions, thank you, Dr. Jana.
Thank you, sir.
And let us go to the next talk by Dr. Lita John. She is from Weather News Incorporated, Japan, and she will be talking about machine learning regression technique applied to improve visibility prediction at airports in China. Welcome.
Thank you. Yeah, thank you very much. Good afternoon, everyone. I was the part of QSAT and also IIT Delhi. Now I'm working in Weather News. It's a private company. We are providing weather information to all the customers like sea, sky, and land. So in this work, I was mainly focused on the visibility prediction. So over the Chinese region using machine learning regression techniques. As you know, atmospheric horizontal visibility is one of the most critical weather variable regarding transportation system, especially within the field of land, aviation, and shipping. But the accurate forecasting of low visibility is still a challenging task for meteorologists. So we have many customers for this type of forecast requirement. So our objective is to improve the accuracy of the prediction values and also reduce the human edit rate. For this task, I started to develop a machine learning model to improve our customers over Chinese airports. So as you know, the existing prediction methods are either with the numerical weather prediction or with the statistical methods. Recently, machine learning techniques are the emerging and suitable method for the low visibility prediction. So for my proposed method is here, I am using the high resolution ECMWF data, meteorological data, and also the metadata trained with the machine learning models and try to predict the low visibility over the Chinese airports. I also added one more parameter, as already you have heard about the importance of air pollution for the fog or haze prediction. So I added the air quality data from ECMWF model, like the PM 2.5 and PM 10 for the prediction of low visibility. By adding these parameters, you can see the improvement of the prediction in the means of quantitatively. So here for this study, I have selected 20 meta stations over China, and I just analyzed the metadata, how the variation of the visibility values during the years starting between 2017 and 2020. So you can see that from during the winter months, especially January, February, and December are the high number of low visibility cases. When I make the threshold to 1000, here also you can see the same pattern. It follows. The major number of low visibility cases are in winter months. So the same thing I repeated for the different stations, how the low visibility is varying. And here with the threshold 1000, you can see that maximum number of low visibility cases are in a special station like ZWW. It is in the northwest side of China. So all other stations also have the low visibility, but as compared with the ZWW, it is less. So I'm not telling much about this observational result. The same thing is repeating for the December, January, and February, same pattern. So as you know, before doing the machine learning model, we need to make a data collection and preparation, analysis, and feature engineering. So by that, I just go through collected different parameters of ECMWF model and analyzed the results and selected just blue colored parameters for the machine learning models. So here you can see that the importance of the air pollution for this type of visibility prediction. The verification measures I used is a confusion matrix with true positives, false positives, and accuracy, recall, precision, threat score with the threshold 3000 and 1000. So you can see the results of ECMWF MLP model for the values for threshold is 1000. When the left side is the ECMWF direct visibility output, and the right side is the ECMWF machine learning outputs. So here you can see that some of the stations are improved using machine learning model without the air quality data. But when I add the air quality data along with the ECMWF's high resolution meteorological data, there is a drastic improvement for some stations like ZWW. Here, here as compared with most of the stations, the improvement is very high as compared with the ECMWF model, and accuracy also very high. So when you compare the time series plots also, you can see that the variations of highs and lows are well captured as compared with the ECMWF visibility data. The air quality, machine learning model with the air quality data is improving a lot, especially in the ZWW station where the number of low visibility cases are very high, and those drastic changes are very well captured with the machine learning model with air quality data. So this station especially very much correlated with the air pollutions like PM2.5 and PM10. The another station is ZSNJ. The same thing is repeating here. You can see the variation of the time series, how the low visibility values are varying. So I have selected some of the fog events of these stations like ZHH and ZSNJ and ZWW. So you can see the comparison between the observation, ECMWF and ECMWF without MLP model, without air quality data, and with air quality data. So most of the fog events less than 1000 meters are able to captured by this machine learning model with the air quality data. So for another stations like ZSNG, here also you can see that the fog events are well captured with the air quality data, but without air quality data, there is not much, not capturing much as well as the air quality data. So only one cases are captured here, but it's not, it's very close to the observation, but it is false positives. So the another station is ZWW, where the number of low visibility cases are very high. So you can see the ECMWF prediction is just 9, not less than, even not less than 3000. But in using the MLP model, we can get around 2000, 3000, that range. But when we use the air quality data, it's improving a lot for this special station at China. So the conclusion and future work plan of my study is that this study shows a good improvement for low visibility prediction at airports in China, and the results shows a ECMWF model with machine learning and air quality data makes a good consistent forecast as in the meta stations, and can accurately predict changes in visibility with thresholds 1000 and 3000 meters. The ECMWF model with the machine learning model without air quality data, it cannot be predict the low visibility values less than 1000 meters, but is consistent with 3000 meters. The overall analysis shows that the atmospheric visibility forecast can be improved using machine learning regression techniques with high resolution meteorological data and also air quality data. So the influence of air particles and meteorological conditions to the prediction of visibility are more complicated. So that I would like to investigate further. So this method can be used all over the world for the visibility prediction of airports and also seaports. So you already heard about the fog cases with air pollutions over the Indian airports. So I think this method will be a good solution for that type of problems. Thank you. So
to Dr. Lita for finishing on time. So let us take a few questions. Anybody?
yes, yes.
So you are in Japan or?
Yes, I'm in Japan. Japan, in Tokyo.
Okay.
Yes, close to Tokyo, Chiba. It's close to Narita Airport, Tokyo Narita Airport. So I was in CUSAT
Yeah.
for,
Yes.
yeah.
So, anybody having questions? So you are taking PM 2.5 as well as PM 10 also as an input for this
Yes.
model. Okay.
Yes, yes.
And you are using artificial neural network?
Yes. So I'm using the artificial neural network model, multi-layer perceptron regression technique.
Okay, multi-layer perception.
Yes, yes.
Okay, then thank you, Dr. Lita, for your nice talk. And I think that machine learning techniques are catching up with the atmospheric science for many problems in the atmospheric science. So,
yes.
So thank you.
Yeah. Thank you. Thank you very much.
Let us go to the next talk. Prashant Kumar Chauhan from Banaras Hindu University. Study of 3 different dust storms characteristics and their radiative properties over Indo-Gangetic basin.
So he's not present.
Okay, Prashant. Okay. So next person is present, Dr.
Yes, sir.
Mane. Okay. So let us welcome Dr. Pratibha Mane.
Yes, sir.
From Ferguson College, Pune. She'll be talking about intricate interactions between stratospheric aerosol layer and different types of clouds.
Yes.
Yes.
I'm audible?
Yeah.
Yes. Topic is intricate interaction between stratospheric aerosol layer and different types of clouds. All of you are familiar about atmospheric aerosols, the suspended particles in the atmosphere. In this study, the suspended particles in the atmosphere are distributed vertically in 4 atmospheric layers. The instrument used for this study is twilight photometer. This instrument, in this instrument, one telescopic system is connected. One telescopic system is used, and detector used is photomultiplied tube. This instrument gives a vertical distribution of atmospheric aerosols from about 6 kilometers up to 350 kilometers with height resolution of 30 meters. This instrument based on the principle that is twilight technique. When twilight starts, the lower layers of the atmosphere goes in the shadow of the earth, and upper layers are still sunlit. The boundary between sunlit layer and shadow zone is called as twilight layer. It is shifting monotonously upwards at the evening twilights and downwards in the morning twilight. The twilight period is 0 degree to 18 degree below horizon. That is near about 82 minutes after sunset and 82 minutes before sunset, before sunrise. The 2 important parameters of this twilight technique are time t and intensity I. These 2 parameters are used to calculate altitude h and aerosol number density per centimeter cube. And this graph shows aerosol vertical profile. As in the troposphere, the aerosol density decreases as height increases, as altitude increases, but in the stratosphere, it slightly increases. This increase is called a jung layer or stratospheric aerosol layer. The height of this altitude of this stratospheric aerosol layer and its aerosol number density is calculated from aerosol vertical profiles, and their relation with different types of clouds are tried to find out. The clouds are classified only in 3 groups: high level clouds, medium level clouds, and low level clouds only. This graph shows the comparison between altitude and aerosol number density of jung layer. This upper graph shows altitude of peak of the jung layer, and this lower graph shows aerosol number density of peak of that jung layer or stratospheric aerosol layer. From these 2 graphs, it is clear that the altitudinal variation of annual variation of that altitude and shows opposite phase relation. In this graph, this black line represent altitude of peak of aerosol stratospheric aerosol layer, and these red spots represents high level cloudy days. These green represents medium level cloudy days, and these low these blue represents low level cloudy days. These high level cloudy days are observed frequently in year 2010, but medium and low level clouds observed very rarely separately. They are observed after high level cloudy days. The one when from this figure, we observed that aerosol this altitude of this stratospheric aerosol layer decreases up to 11 kilometers preceding the high level clouds. It decreases up to 9. It decreases 2 days prior from observing middle level clouds, and 3 days prior observing fog or dewdrops, that is low level clouds. We also calculated aerosol number density of this stratospheric aerosol layer and tried to find out the relation between this aerosol number density of this peak of stratospheric layer and high, medium, and low level clouds. We observed that the aerosol number density decreases 2 times preceding the high level clouds. It decreases 3 times, but 2 days prior to middle level clouds, and it decreases 4 times 3 days prior to low level clouds. We also tried to find out a relation between altitudes of peak of this jung layer and altitude of peak of this jung layer for year 2009, 10, and 11. From this figure, it is clear that there is no variation from October to December, but variations are observed from January to May. And this 2010 year, the altitudes are at lower sides, but in 2011, they are 50% increase. But for in case of 2010, there was 2 times increase than year 2009. Further, these graph represent interannual variations of aerosol number density of this stratospheric aerosol layer for 3 of the years. And here also we observed no variations for October, November, and December months. For January to May, there are variations. For February, there was 25% increase in case of 2010 values than 2009. In March, there are 55% increase. In April, there was 65% increase. And in case of 2011 also, there was 30% increase in March, 55% increase in April, and 10,000. In summary, I will say that the altitudes and aerosol number density of these stratospheric aerosol layer shows day-to-day, monthly, seasonal, and interannual variations. Their annual variation, altitudes and of jungle shows opposite phase relation. We can relate. We cannot relate these jung layer altitudes with these cloudy days with these few events, few data sets, but more data sets are required to arrive at some conclusion and all. Thank you.
Thank you, Dr. Pratibha. So, any questions from the audience? Yeah, I have a question. Actually, how sensitive your this aerosol observations to the cloud? So when that means when clouds are present, whether your observations are how accurate those observations?
Observations are taken at preceding the cloudy days and after the cloudy days. We can't take observations during cloudy days.
Okay.
Because this is passive remote sensing techniques, and clouds are up to 6 kilometer levels, below 6 kilometers, and we are taking observations above 6 kilometers.
Yeah, and another question has come. What does it mean by jung layer? One question has come from the audience.
That is stratospheric aerosol layer. This is found out by Dr. After his this layer is also called a jung layer or stratospheric aerosol layer.
Okay, thank you, Dr. Diva.
Thank you.
Yeah, thank you for your explanation. So I think that comes to the end of this session. Are there anybody?
So there is one more question directed towards Dr. Banerjee, sir, actually.
Yeah, okay.
Shall I read out the question?
Yeah. If Dr. Banerjee is there?
He seems to be there, but I'll just check again. Yes, sir, he's there.
Yeah. So
okay, I'll read out the question now.
Yes.
Can you give some insight on vertical type distribution of aerosols during monsoon and pre-monsoon seasons?
I don't think. Okay. Yeah. Dr. Banerjee?
Should I read the question again, sir?
Yeah, but I don't know whether he's hearing or not. Dr. Banerjee?
I'll read the question again. Can you give some insight on vertical type distribution of aerosols during monsoon and pre-monsoon seasons?
Looks like he's not there at the moment. So anyone else would like to answer, either Dr. Suresh Babu or Dr. Ratnam?
There are no more questions, sir.
Okay, okay. So that brings to the end of this session, and I thank all the speakers for giving their nice presentations and sticking to the
Thank you, chairs, speakers, and audience who have joined in online and offline modes. This concludes today's program in Nila Hall. Kindly join for the release of special poster covers in Pampa Hall by 4:40 p.m. Thank you.